Welcome again to module 9. In this module, we are discussing kinetic model of ultrafast spectroscopy. So far, we have discussed the build-up signal. The process which we are discussing is following. We have excitation by pump from A to S star, and we have only discussed the effect of pump in the build-up signal Na star. Na star is the population in the excited state. So, due to a pulse, we have seen that build-up signal, this is Na star build-up signal, depends on. So, this is the situation where we have only invoked the effect of pump, and the build-up signal depends on the error function, which is given by this equation as a function of T1. So, the basic idea is that I have a pulse time domain representation. This is the intensity profile of the pulse, and this build-up signal depends on the integration from minus infinity to any time t1, and this area under the curve is contributing to this build-up signal. Next, we will discuss excitation of A to S star, A to S star with the help of pump, and subsequently S star photodissociates with a rate constant k. We are not considering probe pulse yet. So, the process which we have, the process which we are going to discuss here is A to S star excitation, and then S star photodissociates to the product with a rate constant k. So, for this process we will be able to write down the rate equation. Rate equation depends on this dN star dt RAS star minus k N star. This negative sign comes because that will decrease, this process will decrease the population of N star. That is why this negative sign. On the other hand, RAS star, this rate of excitation will increase the population of N star. We can rewrite this equation. This equation is strictly valid in the unsaturation regime, where we have assumed that Na, number of population in S state, is much greater than N(S) star. If this is valid, then one can approximately say that N(S) star remains constant, almost constant. This is called unsaturation limit. Now, this equation is the first order linear differential equation of the standard form dy dx plus px y equals qx, which can be solved using the integrating factor e to the power px dx. So, for the given problem, we get the integrating factor e to the power kt. That is why we have multiplied e to the power kt, and rearrangement of this equation we get this very easy to follow. Finally, we would like to integrate it from minus infinity to T1 because we would like to know the build up signal. Ultimate motivation is to find out Na star T1, how this population Na star population is responding. So, this integration can be done, but we have inserted now this RAA star rate of excitation. This expression is obtained before, and this expression is related to this integration from minus infinity to T1 for the normalized Gaussian function. After integrating, we get this expression, and little bit of rearrangement, this 4 ln 2 t square minus divided by delta t square minus kt. This can be written as t square root of 4 ln 2 divided by delta t whole square minus 2 multiplied by t square root of 4 ln 2 divided by delta t multiplied by k delta t divided by 2 4 ln 2 plus k delta t divided by 2 square root of 4 ln 2 whole square minus k delta t divided by 2 square root of 4 ln 2 whole square. So, this can be rewritten, and in the end what I get is this expression. So, this can be written, and finally we get this expression. In order to integrate it, we will assume that this function is x. So, we will be able to get the x1 limit corresponding to t1, and we get this expression for the integral. And this expression is rewritten here, and because it is a Gaussian standard Gaussian integral, we have written it here, and this is nothing but the error function. So, finally, after doing these integrations, we get an expression for the build up signal of Na star under the following situation. I have pump exciting molecules from A to S star, and this S star is dissociating, and the dissociation rate constant is K. So, what we get is that the build up signal definitely depends on the error function, which means there should be some behavior like this. There will be a behavior like this, but at the same time we have additional factor e to the power minus k t1. These are all constants. These are all other components are other terms are constants. So, they will not contribute to the shape, overall shape of the build up signal Na star, but the shape will be controlled by the error function and this exponential decay function. This is now plotted. So, our previous situation was effect of pump. Now, we are considering pump plus photodissociation, both are acting together. In that case, if I have a pulse exciting the molecules to the excited state, we see that the early part of the time is dominated by the error function, just like the one which we have here, but then later part is dominated by the decay. That is the, so this part is dominated by the error function and this part is dominated by the decay constant. Here there was no decay, that is why we did not see a decay in the build up signal of the of Na star. So, this is Na star build up signal as a function of T1. And if we make it K 0, then we get back our earlier equation. So, it is quite clear so far is that excitation by a pulse, when we undergo an excitation by a pulse, build up signal in the excited state would be controlled by an error function of the kind shown here, and if there is a decay or some other loss processes involved, then that would show up in the build up signal as well. Now, we will take a look at the joint action of pump and probe without invoking dissociation. So, our processes are following. We have pump and then we have probe. We are creating positive ion. This is excited state, and we want to find out if we monitor only ion signal by time of flight MS, time of flight mass spectrometer, then how the signal would look like, and that is nothing but the response function. So, we would like to predict that response function when we look at the ion. Here we can remind ourselves that these ions would be observed only when I have population in the excited state, which means if the pump and probe delay, the delay between pump and probe is too long, then it may so happen that A star, we do not have any more A star because it is decaying, and we may not see A plus. However, in this situation, so far we have not discussed, we have not included the dissociation part. We are saying that let us assume that molecules are excited to the excited state, and the moment it is excited to the excited state, it will stay there, and then probe pulse can come and then ionize those excited molecules and produce A plus, and we are going to observe A plus. So, in this case we will be able to write down the rate equation, the ionization rate equation, which is dNA plus dt1. We have to remind ourselves that this variable we have taken as dt1 because Na star, this will depend on the population of Na star, and Na star we have seen so far, Na star population would depend on T1. So, this equation has a variable T1 where we have already seen that Na star T1 can be represented by this integration, and integration, if we do this integration, we get error function that we have seen already, but we will not get the integration done immediately because we would like to convert the final expression for this dNA plus to some other form. So, this dNA, this equation can be integrated, and finally we get Na plus population, which is nothing but an integration from minus infinity to plus infinity. The idea behind pump probe configuration is that an ultrafast pulse is used to excite the molecules, and the second probe pulse, which arrives at a variable delay time, is used to probe or interrogate the temporal evolution of the excited state prepared by the pump pulse by ionizing the excited molecules. Thus, in the ionization detection experiment, the time integrated yield of the parent ion is monitored as a function of the variable time delay upon joint action of the pump and probe pulses. So, we have to clarify this point here, why we are taking an integration limit minus infinity to plus infinity for the ion signal. We are looking at the total ion signal produced due to joint action of pump and probe. We are not interested in the build up signal, not interested in build up signal of A plus. We are interested in total ion signal at a particular delay between pump and probe pulses, and that is why if we are interested in total ion signal produced at a particular delay between pump and probe, we have to integrate it from minus infinity to plus infinity. But here we are interested in the build up signal at a particular time, how much population I have, because that population will contribute to this population, and that is why the integration here is taken from minus infinity to T1, that particular time. So, this integration finally Na plus integration can be rewritten as this. These are the constants we get for the pump and probe pulses, and finally integration we get this integration. And if we would be able to rearrange this integration, because the variables which we have used, remember pump pulse had a variable A, the pump pulse had a variable T, and the probe pulse had a variable T1, and they are related, but we can rewrite this integration as like this, as t1 and t are two independent variables. The integral part of the above equation can be rewritten as this, which can be further rewritten as this, where we are defining tau, which is t minus t1, that is the time delay we will say. So, finally, what we see is that I have two pulses, one of them variable t, another one variable t1. So, the difference delay between two pulses can be defined as tau equals t minus t1. And in terms of tau, the moment we express this expression, we get this. This integral can be written as minus infinity to plus infinity integration I pump, this is normalized, that is why this sign, and I probe t minus tau dt. This is a very familiar expression. It is familiar because this expression is nothing but autocorrelation expression. If we remind ourselves that this, when we did an autocorrelation experiment, we used 50-50 beam splitter, and then we use, this is the Michelson interferometer, and this is the way we got that. So, it was intensity autocorrelation, that is why SHG crystal was used, and finally, this autocorrelation signal, second order autocorrelation was written as a function of tau, which is nothing but minus infinity to plus infinity I pump I probe dt, and that is exactly what we are seeing. So, this expression can be written as an autocorrelation function, and in this figures we have expressed the meaning of tau. If we look at these different figures given here, we are seeing that we are changing tau, which means when they are completely overlapped, tau equals 0, they are fully overlapped. On the other hand, tau can be negative, tau can be positive depending on when the pump and probe pulses are coming in time, and from the pulse measurement, from the discussion of pulse measurement, we have also seen that this, the expression of the second order autocorrelation term is nothing but this. So, the integral becomes minus infinity to tau 1, and here we will assume that this part to be x square, following the same method which we have used previously to get the error function. Finally, we get the error function, and if we plug that in, then finally we get this expression for the error function from this integration. So, finally, we get Na plus DNA plus, sorry, Na plus ion signal, total ion signal we get as a function of tau 1, this tau 1. Tau 1 representing a particular delay between two pulses. So, at a particular tau 1, I will get a particular value for Na plus, which will correlate to the MS mass spectrum intensity. And if I change the delay between two pulses, for each delay will be able to get different value of total ion yield, and I will be able to plot it. And again we are seeing that signal, this is the response function, that signal will depend on again the error function, and the variable is tau 1. So let us look at this variation. We have used a Gaussian pulse here, and we have considered that we do not have k. So A star is not dissociating, we have only pump and probe pulses, and we are creating positive ion. The moment we create positive ion, we can detect it, and we are trying to find out total ion signal. And when you plot the total ion signal as a function of time, what we get is that this is tau as a function of tau 1, then we see that total ion signal would look like this. So if there is no photodissociation at all, then total ion signal would be just like the build up signal which we have expected for the excited state. But what about if we have a dissociation? So now the process is following. I have pump, I have probe is creating positive ion, pump is creating the excited state, and this excited state is decaying to a photoproduct with a rate constant k. So I have a rate constant. In that case, this is going to be tau 1, this is tau 1, this is also tau 1. It is a joint action of pump and probe. So if we look at this, then what will happen? We will see that in the early part, the total ion signal. So we are looking at the total ion signal, and if we look at total ion signal, then it just behaves like an early part would be like an error function, and the later part would be the dissociation. And if the dissociation is very fast, which means rate constant is very large, then what will happen? Will not be able to measure the pulse, will not be able to measure the kinetics anymore, will be able to measure, will end up with measuring the pulse. So if we open the photodissociation channel along with the joint action of pump and probe to model actual experimental observation under ionization scheme, details of the math are not shown here, but in this figure we show integrated yield. So this yield is actually Na plus yield. This y axis representing total integrated yield of A plus. So now this response function, this particular response function explains all the questions we asked in the beginning of this module. It explains why we have a signal in negative delay. This is because of the error function. Maximum signal is not observed at 0 delay, which is also obvious here, and this is the consequence of this error function, the behavior of the error function which dominates the early part of the or the near zero delay part of the response signal. And if we would like to know the k rate constant from this expression, we have to do the math and we will be able to get that expression. In addition to that, if the process is very fast, let us say this photodissociation is very fast. When I say very fast, it means that k is much greater than the pulse width. If this is so, then what will happen, will not be able to measure the dissociation rate constant, will end up with measuring the pulse, and this is an important realization. When I have pulses, the pump and probe pulses longer than the rate constant, which means the process is very slow, and if the process is very slow, the dissociation process or some loss process is very slow, then only we will be able to measure the process with the help of pump probe configuration. If the process is itself very fast, then we will not be able to measure the process, will be measuring the pulse duration, and this looks like an autocorrelation signal. With this, we have come to the end of this present module. In this module, we have discussed different aspects of kinetic model of ultrafast spectroscopy. We have discussed we have discussed normalized Gaussian function, we have discussed error function, we have discussed response function, ionization detection scheme, effect of pump and probe with and without dissociation. We will meet again for the next module.